So we got some interesting results. Um, so we had a group back there that said 2 always wins. Some other group said 2 always wins. And the group up in front convinced them that they're not correct. What happened?
We always made both players greedy, so we didn't sacrifice any triangles. But once you were able to sacrifice, it came out that player one could, in certain situations, player one could be in control.
Is it was it player 1 was winning in certain evens or odds? Okay.
Yeah.
Is that what we found? So we found something interesting up here too. This doesn't satisfy the definition of a combinatorial game because you can actually have a tie, right? If you have an odd number of vertices, then you could end up with each player capturing triangles of an equal number. So that would be, I don't know what's been done on this. I think it's been not that well thought out yet.
Wait, so for the definition, you can play with an even number. Is it then a combinatorial game because it can't be a tie?
Yeah.
So
Wait, but you don't win by the last player not being unable to move, right? So it's like dots and boxes. It's a pseudo combinatorial game. But you can't have draws in any of the combinatorial game. That's a big no-no. So that would say that with odd number of n, this is not a combinatorial game. So I don't think much has been done about this problem at all because I just found it and I've searched everywhere. I went through Columbia's databases. I just took everything I could find. It would be interesting to find the conditions on the odd number of vertices that would imply. My kids get out right now and I always get the call. Something goes wrong. So I think it'd be interesting to find the conditions, what will make a tie. Can you force a tie? If you've ever played tic-tac-toe and known that you can make a draw at the best, that's what you do. You force it, right? So what would be the conditions for the n equals odd to force a tie? There's a well-posed problem to investigate. Okay, so somebody in this group up here was noticing that greedy play was not always the best way to go. Was it your group that said greedy play is not always the best way to go? That's what we found in the past too, that you shouldn't, in dots and boxes, grab the first boxes you can because then you end up with one box and then the other player gets 8 of them and it's 8-1, right? So sometimes you sacrifice the boxes. So when should you sacrifice the boxes? That's this definition of Loony move. I can't give you a solid, rigorous definition yet. I need one more week, I think, to read up on. It's great for me because I get to read something that I don't know much about, and no one seems to know much about. So a triangle is called completable if 2 of its edges have been colored. Smart play suggests a player should always complete a completable triangle. You should always take the triangle unless the position is Loony. So what's meant by a Loony position? I have a picture here of 2 examples of what's a Loony configuration. And what this is called nim string and triangularization of nim string. The configurations are called Loony because the player whose turn it is has choices that put them in control. So if you notice when you play these games, it really does matter who's first player and second player. If you're at a point in the game so that you can choose to be first player or second player, because when you close up a triangle, you're really restarting the game, right? That triangle's out of the game, and it's as though if those vertices are not part of anything anymore. Isn't that correct? So if you close up a box, and closing up that box gives you options because you have to place the next vertice, and you have the option with that next vertex to make yourself an effective first player or an effective second player. You're in control because you can control the rest of the outcome of the game. So how do we get that here? Well, the player who goes next on this configuration has the choices. They could draw here and finish their turn. If they draw here and finish their turn, they're a second player. They're in kind of a second player position. They could also draw these, close up all these triangles. If they draw here, they can take all these triangles and they effectively start the game again as first player. And the other one, they start as second player, right? Because they put a line down and it didn't do anything, didn't close up any boxes. Over here also, they start again as first player because they are closing up these boxes, they can choose to close this up and become second player, or they can choose to leave it open, and then there's still first player here. So that is, whoever's turn it is, they can restart the game, so they're either first player or second player. And that is what they call being in control. Do you remember me giving you a definition of in control? So Loony configuration or Loony position is one where it puts that person who's going next in control of the board. So they can effectively make it so that they're first player or second player. Everything's up to them. So you can actually examine the board and say, is it best for me to be the first player now, or is it best for me to be the second player? I get to choose that. So I want to give you one example of classic NIM, and then I'm going to start all the graph theory stuff next time. Okay, classic NIM, not single pile NIM. Why do I want to show you this? Because classic NIM is used as an example on the games on graphs. And so is single pile NIM, both of them. I want examples. I want definitions, and I want to see a picture with an example. And that's why I'm showing you this, because I want to see that, and you want to see it too. So how does classic NIM work? You start with n piles of stones. For example, I was cursing with Dr. Collar today. Why do they not draw a picture? Just say this is what they mean. So for example, here's my picture. I have here 4 piles of stones, so this is n equals 4. Each pile has a different number of stones in them, and that's allowed. The game is played by each player selecting a pile. So number 1, they have to select a pile, and you can remove any number of stones you want from that pile. You can remove the whole pile if you want. So for example, the first thing is player 1 here is going to select the second row, and they're going to remove all those stones. That's an example of a move. They removed all the stones from that second row. Player 2 now does it. They go to the piles of stones, they choose a pile. They're going to choose this one, for example, and they're going to remove 2. They don't have to remove the whole thing. They can remove any number of stones from that pile. Player 1's going to go just randomly. They selected that first one, and they're just going to remove 3. So those are gone. Player 2, they're going to remove all 4. That leaves that. Player 1's going to remove all only 1. Now you can do backward induction, right? If they take both of them, then player 2 will win, because then they're left with no move. So they're going to only remove 1. That forces player 1 to choose a row, and it's all she wrote. Player 1 wins, and player 2 can't move. What time are we at? Yeah, why don't we play this classic NIM? I just wanted you to play it so you know what it is. I had to tear up sheets the other day. I don't know if you kept those sheets, but break them up, and you can choose. Just make a number of piles and answer whether winning depends on the number of piles you have or the number of tokens you have, and so forth. And see if you can generalize this. Classic NIM is really single pile NIM. There's no difference. Because when I have a pile like this set up, I'm restricting my person so that they can only remove a certain number of stones at a time, right? For example, they could remove 1 stone at a time. That's allowed. They could remove 2 stones at a time. That's allowed. There's certain things that are allowed and certain things that are not allowed. So you can actually map this classic NIM to single pile NIM. And that's why I never cared about classic NIM, because I worked with single pile NIM, and the game theorists told me, oh, they're the same. So I believed it, never looked back. Just play it.
So I guess we'll